In this video, we shall talk about electromagnetic waves. Let's first write down a bunch of important equations that we have encountered before. The first equation is the Gauss's law. It says the electric flux through a closed surface equals the net charge that is contained within that surface over epsilon naught being permittivity of vacuum. The second equation is what is known as Gauss's law for magnetism. So the magnetic flux through a closed surface is always zero. This indicates no magnetic charge. Magnetic charge in the sense of magnetic poles, north or south, cannot exist separately. They must always appear in pairs. The third equation is what we call the Faraday's law, which states the induced EMF within a closed path equals the rate of change, or rather minus the rate of change of magnetic flux. We recall from our previous video that induced EMF can be written in terms of electric field. The final equation is what we call the Ampere's law, that states a line integral of magnetic field around a closed path equals the following: mu naught conduction current plus the part that comes from the displacement current. Like that. We note that this is the electric flux through a given surface area. This set of four equations are known as Maxwell's equations. Maxwell's equations are the backbone of electromagnetism. Let's concentrate on Faraday's law and the Ampere's law. Let's look at the Faraday's law. Within this magnetic flux, there is magnetic field. So when the magnetic field changes with respect to time, what this equation is saying, it creates an electric field. Now let's look at Ampere's law. This is electric flux, which can be written roughly like that. And that equation says whenever electric field changes with respect to time, that creates magnetic field. So what we have here is when either an electric or a magnetic field is changing with time, a field of the other kind is induced in adjacent regions of space. So the change in electric field creates magnetic field. Let's put a vector notation there. And likewise, the change in magnetic field with respect to time creates electric field. So this is as if you have some kind of electromagnetic disturbance consisting of time-varying electric and magnetic fields that can propagate through space from one region to another. Such a disturbance, which have the properties of a wave, is known as the electromagnetic wave. Examples of electromagnetic waves are radio waves, visible light waves, X-rays, microwaves, just to name a few. So let's see how this works. Let's assume at some moment there is electric field in that direction, and there is magnetic field in that direction. These fields are oscillating up and down along y and z axis respectively, and also in time. So let's look at the electric field first. It is a function of time and position. Let's call it POS for the moment. As time progresses, this electric field the magnitude of it will go less and less, and at some point it will flip, and the magnitude of it will get smaller and smaller until it gets above the positive x-axis, like that. And this process will go indefinitely. At the same time, the magnetic field would oscillate in that manner, and its magnitude will get smaller and smaller until it flips to the other side. And this process will just keep on going indefinitely as well. We note that the oscillation of electric field is occurring on the xy plane, while the oscillation of the magnetic field is occurring on the xz plane. So at any point, the electric field and the magnetic field is always 90 degrees with respect to each other. So the magnetic field is also a function of time and position. So what you can see is the result of Maxwell's equation. The changing electric field creates magnetic field, and changing magnetic field creates electric field. They sustain each other. So such a electromagnetic disturbance creates a wave that propagates along the x-axis. Since both electric field and magnetic field are perpendicular to the direction of propagation, this wave is a transverse wave. So the electromagnetic wave is a transverse wave. Using the right-hand rule, we can work out this direction, namely the direction of propagation. It is parallel to the direction of E cross B. Using the right-hand rule, when you cross or curl your right-hand fingers from E to B, your right-hand thumb will point rightward. So that is the direction of the propagation of this electromagnetic wave. And to maintain this direction of propagation, when E flips, B must flip also. So when you apply the right-hand rule from E to B, your thumb is still pointing to the right. Since these oscillations are sinusoidal, the expression for electric field as a function of position and time is as follows. E naught is the amplitude of the maximum value of the electric field times sine omega t minus kx. Omega is the angular frequency. It can be expressed in terms of the usual frequency in hertz as 2 pi times frequency in hertz. K is the wave number, which is related to the wavelength of this wave as 2 pi over wavelength. And together, the speed of propagation, c, equals frequency times the wavelength of that wave. We note that the direction of that electric field is j hat. Now we see that you have a minus sign here. There's a minus sign here because the direction of propagation of that electromagnetic wave is along the positive x-axis. And since the wave travels along the x-axis, the position is represented by the x-coordinate. We can write down similar vector expression for the magnetic field. The amplitude of the magnetic field is B naught. That's a maximum value for the magnetic field. It's sinusoidal, sine omega t minus kx. The direction of the magnetic field is along the z-axis, so that means it's k hat. The argument of both components are the same because they belong to the same electromagnetic wave. We can even write down the connection between E naught and B naught, and it's given by E naught equals c times B naught, where c is the speed of this electromagnetic wave. In vacuum, empty space, that is, the value of c is 3 times 10 to the power 8 meter per second. So this is what speed of light is, since light is a form of electromagnetic waves. Any electromagnetic wave travels with this much speed in empty space or in vacuum. Since the direction of propagation of electromagnetic wave in this case is that way, we can define a vector quantity that describes both the magnitude and direction of the energy flow rate. After all, waves carry energy, and they carry energy in the same direction as the direction of its propagation. And this energy flow rate is described by the following vector. It's called the Poynting vector. Poynting vector, and its expression is parallel to that direction. Specifically, it's given by 1 over mu naught. Mu naught is permeability of vacuum if the wave is propagating in vacuum, times E cross B. And you see the direction of this Poynting vector is the direction of the propagation of that electromagnetic wave. The magnitude of this Poynting vector gives the flow of energy through a cross-section area perpendicular to the propagation direction per unit area per unit time. So the unit to quantify the magnitude of the Poynting vector is joules per meter squared per second. And since joules per second is just watts, you can also quantify the Poynting vector as watts per meter squared. So now it's clear that the magnitude of the Poynting vector measures the rate of energy flow per unit area. Let's look at the following problem. A laser emits a sinusoidal EM wave that travels in a positive y direction. The frequency is given by that in hertz. The magnetic field is along the x-axis with amplitude 5 times 10 to the power minus 4 Tesla. What are the vector expressions for E and B as functions of time and position? Also, find the average magnitude of the Poynting vector. So let's do the magnetic field first. We know it is directed along the x-axis, but the wave travels along the positive y direction. So Ty equals the amplitude, which is 5 times 10 to the power minus 4 Tesla, that's given right there, followed by sine function, sine omega t minus ky, y here because the direction of propagation of wave is along the positive y direction, so therefore the minus there. Since the magnetic field is along the x-axis, so you should include I hat, the unit vector along the positive x-axis. Now let's determine omega. Omega is 2 pi f. So f is given as 6 times 10 to the power 13 hertz, and that's going to give you 3.77 times 10 to the power 14 radian per second for omega. Now let's determine the wavelength. Wavelength is given by speed of light in vacuum. Let's assume that the wave propagates through vacuum over frequency. Speed of light through vacuum is 3 times 10 to the power 8. Frequency is 6 times 10 to the power 13 hertz, and that's 5 times 10 to the power minus 6 meter for the wavelength. That means the wave number is 2 pi over lambda, so 2 pi over 5 times 10 to the power minus 6, and that will be 1.26 times 10 to the power 6 per meter. Substituting omega and k in here, we have that expression for the magnetic field. Now the electric field. E as a function of time and position y is amplitude. The amplitude is given by c times the amplitude of the magnetic field. So c is 3 times 10 to the power 8. B naught is 5 times 10 to the power minus 4. And that's going to be 1.5 times 10 to the power 5 volt per meter. So that goes in here, 1.5 times 10 to the power 5 for the amplitude of the electric field. And the rest is the same, 3.77 times 10 to the power 14t minus 1.26 times 10 to the power 6y in the direction of k hat. Because when the electric field is this way, along the z direction, and the magnetic field is along the I direction, x-axis that is, when you curl from E to B, you get the direction of propagation in positive y direction. Now the average value of the Poynting vector, it's defined like that, E cross B. So the average value of the Poynting vector is 1 over mu naught times the amplitude of the magnetic field, amplitude of the electric field, and times the average value of sine squared, and that is half. Using the known value for mu naught, you get 2.98 times 10 to the power 7 watts per meter squared for the average magnitude of the Poynting vector. And that solves the problem. Thank you for watching.